Now we are going to take some examples on the how to calculate the steady state errors for different type of inputs. So in this example, we have three type of input. We have the step function, ramp function, and also parabola functions. So you can see here step function, ramp function, and parabola function. And we have the transfer function, which is GS here. In order to find the steady state error, we need to apply the formulas that we have in the previous table. Okay. So for example, here in the case of the input is the step function, so ESS will equal to 1 over 1 plus Kp. This is the main formula, or it can be 1 over Kv or 1 over Ka. So this is the value of the steady state error for different type of input. This one is for the step function or using the position constant. Here for the ramp function using the velocity constant. Here for the parabola function using the acceleration constant. So this is the main formula. But if we see here, the magnitude of the function is not one like in the original when we find the original formula here. So the magnitude is multiplied by 5. So when we convert this one into frequency domain by using Laplace transform, it will be 5 over s. So the value of 5 here will be both here. Okay. So the value of the 5 or the magnitude of the function will be appear in this in the numerator of the steady state error. So when I convert this one, it will give you 5 over s squared. How we convert using Laplace transform? We just use the table that existing in chapter 2, which lists how to convert the different type of function from the time domain to frequency domain, or how to find the Laplace transform. Okay, the last one will be like 10 over s cubic. So this will be the Laplace transform of 5t square ut. You just go through the table, you will find it like this one. Okay, so always the magnitude here will be placed on the numerator of our transfer function. So this become 5 over kv, and here become 10 over s square or 10 over k. Okay, so this will be the new formula that we need to use in order to calculate our steady state error. How to find kp here? Kp will equal to limit s goes to 0 gs. Kv will equal to limit s goes to 0 sgs. Then Ka will equal to limit s goes to 0 s square gs. Okay, now what is the type of our system here? As you can see here, we do not have any s or any integration for this transfer function. That means there is no pools at the origin. There is no s here. That means the system is type 0. Since our system is type 0, that means no integration, we are going to get the values that we already mentioned in the table for the type 0 case. Okay, so after you calculate this value, you just compare with the value in the table of the formulas. Okay, so for the first input, which is 5 over s here, we are going to find the error, which is 5 over 1 plus kb, and the kb equal to limit s goes to 0 gs. If you substitute for each value of s by 0, this will be 0, this will be 0, this will be 0. So we have 120 times 2, it will give you 240 over, and you over 3 times 4, it will be 12. So 240 over 12, it will give you 20. So this 20 here plus 1 will be 21. So 21 here, 5 over 21. So this is the value of the error or steady state error for the first input, which is 5 ut. If you go to the second input, which is 5 over s square, so s square here, I mean, when we talk about 5 over s square, that we are going to find the value of kv, and kv is limit s goes to, in this case, kv will equal to limit s goes to 0 for s times gs. Okay, whatever is the value of gs here, since there is no s in the denominator, so this s will be stay there. If the s stay, that means the kv value will be equal to 0. If the kv equal to 0, then the error or steady state error will be 5 over 0 will be infinity. Okay, so the second input, for the second input, which is 5 ut, your or the steady state error of the system will be equal to infinity. Okay, the same case for the third input, which is 5tu square. So the Laplace transform is 10 over s cubic. Okay, so since it is 10 over s cubic, that means the value of k also here will be s squared times gs. There is no s in the denominator here, so s squared will be 0 squared times any value, it will give you also 0. So the value of k also will equal to 0, and the value of the error will be infinity, as you can see here. So in the first case, for the second one here, infinity, and for the third one also it is infinity. So 10 over 0, it will be infinity. So this is how to find the steady state error for the type 0 system when we do not have any integration in the transfer function of the system. In the second example here, we have one integration, and when we have one integration, that means our system is type 1. So if your system is type 1, and this happen if the transfer function of the system has one s in the denominator here, not this s, the s at the origin, that means s at 0 or at the origin of our system. So here we need to find also, we repeat the same input 5ut, 5t square, and 5t square ut, or the same. So first we need to verify that the closed loop system is stable. Okay, so if the system is stable here, if our system is stable, that means we can go further to find the value of the steady state error. If the system is unstable, no need to go for further analysis for the steady state error. Okay, as you can see here, after we find our system is stable, we need to find the value of kp, kv, ka. When we find the value of kp for the input, we use it with the steady state error for the first input, which is the value of 5 over s. So as you can see here, kp will equal to limit s goes to 0 gs. Okay, so this will equal to limit s goes to 0 to the value of gs, which is as you can see here, sorry, as you can see here, it is 100 s plus 2 s plus 6 over s, and so on. Okay, since you have the value of s here in the denominator is 0, so this the denominator of the transfer function will be 0. Then the value of kb will be a number over 0, so it will be infinity. That means the value of kp will be infinity here. If kb will give you as infinity value, that means the steady state error will be 5 over 1 plus infinity. So it becomes 5 over infinity, which equal to 0. So the error is 0, or the steady state error is 0 when the input is 5 over s. When we go for the next type of input, which is 5TUT, which is 5 over s square, and in this case, we need to find the value of kv, which is limit s goes to 0 sgs. That means we have s times gs. So the s here will remove the original s of the system. So this s, I have s here in order to find the value of kv, I mean kv. So s will multiply by s. So this s will be removed. With that s, we still have a number here. Number is 0 plus 2 is 2, 0 plus 6 is 6, 6 times 2 is 12, 12 times 100, it will be 1200, correct? So the numerator will be 1200. The denominator here, this one will be 0, 3, 0, 4, so 3 times 4, it will be 12. So the value of kv in this case will be 100. If the kv equal to 100, that means your steady state error will be 5 over 100. It will give you 100 over 20, which is a small value actually, and it shows that the system is work with with a good margin of steady state error. Okay, we go to the third input, which is 5tu square ut, and which give you the Laplace transfer of 10 over s cubic. So we apply this input actually for our system. Then we find the value of ka. Ka will limit for s goes to 0 s square gs. Okay, since you have s square, that means you have s square times You have one S here because the system is type 1. Okay, so this S will remove with that square. We still have one S in the denominator here. If S equal to 0, the whole Ka will equal to 0. So Ka will give you a 0 value. So ESS will give you 10 over 0, which equal to infinity. So this is how to find the steady state error for the input of the parabola function, which also give you her infinity value. So you can see here, for the first input we have 0 error. For the second input we have 1 over 20. For the third input we have infinity. That means for the third input, the first order system, it has very high steady state error. For the second or for the ramp function, we have a finite amount or finite number of the steady state error. And for the for the step function, there is no error, and the value of the steady state error is equal to 0. This another class exercise, and this exercise also show you different type of the system. So the first system is type 0, the second system is type 1, the third system is type 2. This all depends on what is the value of S here, n. So here n equal to 1, here n equal to 2, here n equal to 0 because there is no S. Okay, so we call it type 0, type 1, type 2. Okay, evaluate the static error constant and define the expected error for the standard step, ramp, and parabola. So also the same, want to test the three systems for different value of the input. Step function, which is 1 over s. Since he said standard, that means the 1 over s1, 1 over s cube square, and 1 over s cubic. So we need to apply the three type of the input to the three type of the systems. So the first system, we are going to apply the three inputs, and we are going to find the value of ESS, or the steady state error. The same will be repeated for system type 1, same will be repeated for system type 2. And here is the summary for this calculation for the three system. So for the system A here, we need to find the value of Kp, Kv, Ka. Kv equal to 5 point, actually from the formula limit s goes to 0, we need to substitute for all value of s by 0, so we can find the value of Kp. And from the value of Kp here, we are going to find the value of the steady state error in this case, which is 0.161. Then we repeat it for kv, which is sgs. So sgs will give you 0. If sgs is 0, that means your error will be infinity. If k equal to 0, your error will be infinity also again. This is for the first system. All steps are repeated for the second system. The same formula that we use for the first, we are going to apply that for the second. kb, kv, ka for all cases. We calculate based on the formula. We substitute the value of gs from the value here. This is gs in the first system. That one is gs for the second system. That one is gs for the third system. When we say limit s goes to 0, that means each s here will be replaced by 0 to find the value of kp, kv, and ka also. And this one is for the third system, which is type C. Also the same, we have kb equal to infinity. If kb equal to infinity, that means your error will be equal to 0. If kb equal to infinity, that means your error equal to 0. If ka equal to a value here, which is 875, your error will be also a constant or a finite value. So this for the three different of inputs and three different constants, we got three different steady state error for a system: 0, 0, and also constant number, which is 1.14. Okay, so all these steps actually are repeated in any case we want to find the steady state error after we know or we confirm that our system is stable, and we need to find its steady state error.